I'm your host, Dr. Matthew Richardson, and welcome to another stream of CosmoQuest Astro 101. So, in our discussion last, what was that, Friday, we were talking about being able to colonize the galaxy. But during that discussion, there was a lot of talk about what would happen if there were relativistic effects at play. So I figured that today we're going to be talking about time dilation in its many forms. So here I'm showing an image of one particular type of time dilation, which is known as relativistic time dilation. In this scenario, what we have is a stationary observer, and we'll demonstrate it by a person that's on Earth, relative to a person that's in a spaceship that's traveling at some speed v, where v is greater than 0. And the idea is that simply due to the fact that the traveler is moving, he experiences time differently versus the person that's on Earth and is at rest. And so with this scenario, in the top portion of this diagram, we're kind of seeing two people. If you want, you can imagine them to be twins. One person is going to remain on Earth. The other person is going to get into a space shuttle, and they're going to synchronize their clocks to be at the same time. The person on the space shuttle is going to make some round trip going out to some distance at some constant velocity, then return, and what you get upon returning is that the person that was on the space shuttle has aged very slowly. However, the person that remained on Earth, as you can see in the diagram at the very bottom, is now really much, much older. And this is simply one of the results from special relativity. And it's known as relativistic time dilation. And so I figured that I would want to also, of course, explain it, but also do a problem where you can see the math in action for this particular phenomenon. Yes, person B will now need to respect his elder. That when he initially left was his fellow colleague or friend. All right, so let's go ahead and bring up I think this is it right here. There we go. And so I quickly worked through these problems prior to the stream, so I think the math should be all good. I was able to check at the very least, and I think the math should be just fine. Let's go ahead and walk through this problem of what's going on. And so I want to go here. There we go. So here's the problem. Humanity has achieved the long-sought goal of relativistic travel and has a spaceship that can travel at a velocity v of 0.9 c, which is basically saying that we're traveling at 90% the speed of light. They wish to run a test by doing a round trip to the nearest star system. Assuming that the interstellar spacing between stars, which we're going to denote as the variable d, is 1 parsec, which is equivalent to 3.26 light years, how much time will have elapsed for travelers aboard the spaceship, like in our diagram we just saw, versus observers on Earth? And so, to be able to start this problem, you need to be able to at least start off with calculating the amount of time that's elapsed, either for the observers on Earth or for the observer on the spaceship. In this situation, we're going to do everything from Earth's perspective. So, or the Earth observer's perspective. So the very first thing we're going to do is determine the amount of time required for the round trip. And so it's a very simple calculation. The time for the round trip, of course, is the time it takes to get to the destination the astronaut's going to, and the amount of time it takes to return. Assuming that the conditions for the travel are the same going and returning, the amount of time it takes to go versus the amount of time it takes to return is the same. So we basically get an equation where we calculate that the amount of time going is the distance traveled divided by the velocity at which the spaceship is going at, which we're given in our problem, and you simply multiply that times 2. And given the conditions we have, we end up getting a final result that it takes 7.24 years for the total round trip as observed from the observer on Earth. So from there, And I wanna make sure that I'm able to keep up with comments too while I'm doing this. So let's do that. Let's bring up the comments as well. So from there, we can now go ahead and start determining, well, how much time will have elapsed for the person that's on the space shuttle. Well, there's an equation that allows us to do this transformation of relative times. And the equation is shown here, where we have delta t is equal to some gamma factor or Lorentz factor times delta t naught or delta t sub 0. So delta t corresponds to the elapsed time for the observer that's at rest. Delta t naught corresponds to the elapsed time that the astronaut experiences. And lastly, the gamma factor or the Lorentz factor is the conversion factor which allows us to go from the two different time frames. And it's given by the equation I'm showing here. All right. So with that said, we can go ahead and continue our problem to now solve for, well, in this case, we're going to solve for the elapsed time for the astronaut or the moving traveler in the space shuttle. So we need to solve for delta t sub 0 or delta t naught. Those are one and the same. So solving for delta t naught, we do some really easy going algebra, and we finally obtain a result that corresponds to 3.19 years that the astronaut has observed as far as the elapsed time going and coming back from his round trip. So what you kind of notice, well, percentage-wise, we're saying that the amount of time that's elapsed for the astronaut is 44% of the amount of time that's elapsed for the person that stayed on Earth. Or another way of putting it, it's almost roughly half the time, somewhat close to it, not exact, but almost half the time has been cut down for the astronaut versus a person on Earth. And so, and of course, this effect will be even greater if you consider the fact that if the person's speed on the space shuttle increases, you're going to get an even more drastic effect with this amount of time that's different between the two people, the person on the Earth and the person in the space shuttle. And so I see I have a question here. Yeah, 7 years would be amazing. I agree with you. And of course, this assumes that we've achieved relativistic travel. So Hanny asks, what if they were transmitting video the entire time? Would it be slow coming and going, and normal when they pit stop? So if they were sending signals, if they were sending information to one another via light, according to special relativity, light is a constant in vacuum. So the actual transmission of the video would not be slower or faster. It would be the speed of light. However, if you start considering the fact that they might get farther and farther away, once you get to a certain distance, of course, then the frequency of the light can change, and you can get into other types of effects from well, of course, that's like over very large distances. Binge watch TV in half the time. Of course, if you're watching everything, um, but would the video look weird? So yeah, there's relative motion between the two, right? So you would have Doppler shifts at play. So the frequency of the light would change as a person, for example, from Earth is streaming the information to the person that's on the space shuttle. But as far as the physical speed of the light, it remains the same. Of the transmission, it remains the same. And so I would assume, actually, now that I think about it, I mean, TVs are said to be able to acquire information at a particular, frequency range. So yeah, the video might begin to look weird to the point where you can't see it at all. because you've probably moved far enough away from the person, or it's actually all relative velocity for Doppler shift. So if you're maintaining the same velocity, relative velocity, then the amount of change in frequency will be the same, actually. So it really depends heavily upon their relative velocities to one another, or the relative velocity between the two people. That is, the observer on Earth and the person in the space shuttle. Oh no, the webcam froze. No. Well, in the event that you guys missed it, I was basically saying that while on the space shuttle, the person's moving at a constant velocity. And so that relative velocity, right. So that relative velocity will ultimately determine the Doppler shift. And that Doppler shift would remain the same. All right, so that's actually the first half of the problem for today, which was basically the idea that if you have a person that's in motion, or a clock that's in motion relative to a person or clock that's at rest, the clock that's in motion will experience time much differently from the person at rest. The amount of this difference between the two clocks is heavily dependent upon, in this case, the relative speed between the two um, clocks. In this case, the faster the relative speed, the more the difference will be. And so I kind of figured that that would be the first part that we could talk about, which is relativistic time dilation. The next part that I want to be able to talk about is what's known as gravitational time dilation. So what I'm going to do here, let's switch up let's move that out the way, and where are you? There we go, gravitational time dilation. So I want to move this one out the way as well, and I want to bring, oh wow, I just realized you guys could not see at all. Nope, you guys could see it. Never mind, that's the internet. All right, you guys could see the equations that I was showing earlier. All right. Well, the next thing we're at right now is talking about gravitational time dilation. Um, Now, with gravitational time dilation, or time dilation due to acceleration, um, we now have stepped outside of the realm of special relativity and have moved into the realm of general relativity, as you need general relativity to explain this type of time dilation. And so the idea here is that if we start on with the left hand panel, with that diagram, we kind of see that we have two scenarios. We have essentially the top scenario, and we have the bottom scenario. In the top scenario, we have motion that there's no sort of acceleration with this motion. So constant velocity. And we kind of see that the clock moving from as you move from the left to the right, the clock looks like it goes around, let's say for example, like 30 seconds or so. However, in the case with the motion undergoing some sort of acceleration, if we imagine that that red curve at the bottom corresponds to a person's motion, we can clearly see that they're undergoing some sort of acceleration here. And that due to that acceleration, their clock actually registers a total elapsed time that's much less than. In this situation, noting that the clocks were synchronized initially, at the very end of of the travel for that curved red line, we end up getting the situation where the clock has only went, like for example, like 15 seconds versus 30 seconds for the um for the constant velocity motion shown at the top. So that's one way in which we can have this um this time dilation due to some difference in acceleration. Now the other one is going to be due to difference in position relative to some gravitational potential well. And so in this situation, this is an actual. Well, both of them are realistic, but this is one that's been tested and proved to be true. If you could imagine that you have an observer on Earth with a clock, and you have, for example, some observer or clock that's stationed much farther away from the surface of the Earth, like for example on a mountain or in space, you'd clearly be able to say that, or you could say with confidence that the gravitational pull on the person on Earth is much greater than the gravitational pull on the person that's much higher up, or especially if in space. And that's only because the gravitational force on the body, of course, drops as 1/r². So the idea here is that at the very bottom for the right panel diagram, at the very bottom, we have a person or we have a clock that is much closer to the surface of the Earth. And then at the very top, we have a clock that's much farther away from the surface of the Earth. So their relative position relative to Earth's center is different, which means that the gravitational potential in the two is different. Now you notice that with the situation on top, the amount of time that elapses is much greater than the amount of time that elapses for the clock that's closer to the surface of the Earth. In this situation, we have what's known as gravitational time dilation, where for people that live, or for clocks or people that are closer to the surface of the Earth, the amount of time that elapses for them is much slower than a person or clock that's much farther away from the surface of the Earth. Oh man, is everyone having this issue with my image freezing? Hopefully not. I'm happy you guys can still hear me though. All right. Okay, it was only for you. All right. All right. So we're gonna continue going. We're gonna go ahead and jump into the next problem. An example problem of gravitational time dilation. So I need to go back here and bring up the next problem. And so with this situation, we want to be able to use some of the same conditions that we used in our previous problem for relativistic time dilation. And so we're going to assume that during our test run, and this is going to sound probably familiar to some of you guys, but during our test run, we crashed on an Earth-like planet in the star system described above. And we've been stranded there now on this planet for 3.19 years. If you notice, 3.19 years was the solution we got for our previous problem. So upon taking a trip to a region above the atmosphere, you notice that the system is a binary system where one of the components is a solar type star, which is good, you know. Solar type star, Earth-like planet, everything is great, right? However, the other component of the star system is a black hole. So this is kind of like reminiscent of, if any of you guys have ever seen Lost, the reboot of Lost in Space, this is exactly the situation they were in at the very end of the first season. So, assuming the passage of time on Earth has been 7.24 years, again, we're using the same time conditions that we used with the relativistic time dilation problem. And you are at a distance r of 1 AU from the black hole. How massive must the black hole be to cause such time dilation? For this problem, we will be using the following equation. And of course, the equation looks exactly the same as the equation we used for relativistic time dilation. But the only difference now is that our gamma factor is not the Lorentz factor. It's similar in nature, but it's different in functional form. So basically, now we have to take into consideration the gravitational potential that's due to the mass that's causing the time dilation, which in this case is the black hole. And so we modify our equation slightly to get this gamma factor. And so moving on from there, of course, we can go ahead and solve we need to solve for, we need to be able to extract the mass from this equation. So, and hopefully you guys can still hear me. I think I'm starting to see what's going on here. My connection seems like it keeps it gets worse and it gets better. So hopefully everyone's not being heavily affected by that. But basically, we have to be able to extract the mass of the black hole from the gamma factor that we have here in front of us. So solving for gamma in terms of relative to the times that we've talked about before, where in this case, delta t corresponds to the time dilation that you experience on the planet versus delta t naught, which is going to be, or better yet, and sorry, no, that's wrong. Delta t corresponds to the amount of time that's elapsed for an observer that's on Earth. And delta t naught corresponds to the amount of time that's elapsed for you while on the planet. And so solving for gamma, or basically replacing gamma with its equivalent of 1 over the square root of 1 minus the fraction of 2gm divided by rc squared. And if you guys can notice, this equation is actually it's essentially almost exactly the same as the equation for gravitational redshift. And so solving for the m with some cool algebra, we finally come up with the solution of the mass for the black hole being 40.5 million solar masses. After, of course, some unit conversions, or a unit conversion. Well, this is actually very interesting because like I said, I was building this problem up, shortly before the stream started, and so I was curious to ask the question, or I wanted to know. Let's see the comments here. I wanted to know, given this mass for the black hole, and given our position relative to the black hole, Hanny, you're heading exactly where I want to go with this. Would a black hole that size fit into an AU? So really what we need to start asking ourselves about is, what is the Schwarzschild radius of this black hole? And given the fact we're a distance of 1 AU from its center, have we crossed the event horizon, essentially, which is what the Schwarzschild radius lets us know. And so this is actually I figured this would be a very interesting thing to solve for, but like I said before, I ran out of time and couldn't get around to actually doing it. And so this is pretty much what I wanted to be able to present today. And so I'm going to go back and see if I may have missed any questions or comments. I've been trying to keep up with the questions and comments while talking. And again, guys, I apologize for the disruptions from the connection I'm having here at home. Hopefully, I don't have these issues anymore for the rest of the stream. So yeah, to solve for whether or not a black hole would be able to. Okay, but just the mic just went a little bit crazy. Okay. So, so would a black hole this size fit into an AU? To be able to solve that, and off the top of my head, I think we actually slightly have the equation for it. You essentially would need to solve for the escape velocity equation for a black hole, which you can actually get from equating centripetal. I think it's centripetal acceleration versus gravitational acceleration due to gravity, and you can get a function that would allow you to be able to solve for the Schwarzschild radius, assuming that the escape velocity is equal to c. But yeah, you can determine whether or not that's the case. And honestly, I don't off the top of my head, I don't know. I guess I can quickly try to do something with it though. Let's do this because I'm actually, like I said, I was curious about this before. So I'm gonna open up a web browser and we'll move together to do this. And so I'm gonna type in. Let's see. And I hope I'm spelling this right. Let's hope that there we go. Google always knows what we're thinking. So the Schwarzschild radius. Let's see if I can get an equation for it. Oh, that would have been very interesting. Another way to do this is okay. There we go. So let's blow this up, and you guys can see it as well. Perfect. So given our mass and our gravity, I'm going to ignore that factor of 2 and see if I can. All right. So G was what was that, like 7 times 10 to the negative 11? Yeah. Let's just round it to 7 times 10 to the negative 11. Um, the mass is, and I can't use this in solar masses because it's gonna, the units aren't going to work out too nicely there. So going back to in terms of kilograms, it's something that's like on the order of roughly 10 to the 38 kilograms. It's close to it, not exact. And I'm getting these values just to let you know because I don't want. I'm getting these values from the actual PDF for the math I solved. You'll see at the very bottom, the second to last line. Let's scroll. There we go. So second to last line states 0.8 times 10 to the 38 kilograms. And I'm just going to round that to 10 to the 38 kilograms to make the calculations easier. And so using that information and noting the fact that the speed of light is 3 times 10 to the 8 meters per second squared, so everything's going to be in SI. Um, so 10 to the negative 11 times 10 to the 38 should give us 10 to the 27. 10 to the 27 divided by 10 to the 27 divided by 10 to the 16. 11. 10 to the 11. So 10 to the 11. And we had 7 divided by 3, which is like 2. 2 times 2 is like 4. So 4 times, I think, 10 to the 11. And this has to be in units of meters. So 4 times 10 to the 11 meters. And so what we want to do there, of course, is compare that to an 8. Well, no, 4 times 10 to the 11. An AU is like, I actually have an AU somewhere here. So let's go back. I have an AU somewhere here. Remember, 4 times 10 to the 11. Where's my AU? Ah! So there we go. Our AU is 1.5 times 10 to the 11. So actually, we're within the Schwarzschild radius of this black hole. And so this is actually not a plausible situation. Assuming, of course, all of my rounding and stuff is correct. Um, what is that? We're like almost close to like a factor of 3. A third or 2/3 in, if I'm getting that right, or 2/3 in the black hole. So yeah, we're dead. So this is actually not a plausible situation for this to work out. You wouldn't be able to measure any sort of time because you'd be dead. Um, the planet itself would probably be like, yeah, we'd be dead. We'd probably undergo a little bit of like spaghettification and stuff, and so. But nevertheless, it was a very interesting idea. Wait a second. Let's see. So yes, the escape velocity for a black hole is different from other objects. The escape velocity for a black hole is always the speed of light. Um, so whenever you solve for escape velocity, you just replace it for you'd replace the v with a c. Hey everybody. So this illusion, I think so. So black holes are a lot more massive, and gravity is based off of mass. So yeah, for black holes, actually, we did this. We looked at the short shout radius for different compact objects in one of our past streams. And the thing about it is that you can actually write a form for the short shout radius that's density based because of the relationship between mass and radius for um, for a black hole. Or wait, is that right? Density? Yeah, well, everything can be density based. But I think no. What I meant to say is you can put everything in terms of mass. I believe for a black hole. I might be getting my words mixed up here, but I remember us doing a calculation in the past for it. So is this a supermassive black hole? I don't believe this would be considered a supermassive black hole. Um, Supermassive black hole, I think, is like on the order of like billions of solar masses. And so I'm seeing there was a link here. Hey, Astro. So yeah, there's different forms you can get for that short shout radius. When you're considering the object to be a black hole, and they might even show it here actually. So you guys can see what I'm looking at, of course. Um, you can solve. You can solve for. I had a thought, and it's like it's the thought is now like slipping away from me. But I do remember us doing a calculation, and I can't remember exactly what the calculation was with black holes. Oh, wait a second. I think the situation we were doing was gravitational lensing. I think that that's what we were doing, and we were doing it when we have light traveling near a black hole and other massive objects like neutron stars or other very dense objects. And so, guys, that's pretty much what I wanted to present today. Um, I'm going to definitely be looking in the chat for questions and stuff. Would you suffer contraction around a black hole, or just so? If you're in the presence of a black hole, you can not so much contraction, but a stretching of the body can happen, as well as time dilation. Wait, even without the tidal forces of a small black hole, I am. Wait, are you talking about length contraction? Um. Well, the issue I would have if you're in the presence of a black hole, um, as far as length contraction is concerned, assuming that you're not in some sort of accelerated reference frame and you're in an inertial reference frame. Well, with length contraction, you can imagine with a ruler, right? If you have a ruler that's moving at some speed v relative to you, that ruler will undergo length contraction. And of course, the ruler itself has to be in an inertial reference frame, and so do you. And what I mean by inertial reference frame is that you're basically moving at a constant velocity, whether that velocity be zero or be some other constant value. Both you and the ruler would have to be moving at constant velocity to apply the rules of length contraction. Um, so the way in which you should think about it is if you have a ruler of some length L, if that ruler has some relative motion to you, then in your rest frame, that ruler is undergoing length contraction. And the amount of length contraction is dependent upon the relative velocity between you and the ruler. So you so if there's a clock on the ruler, then you could consider both the situations of length contraction and time dilation. Dilation. I keep saying dilation. Dilation. So not even so much as moving fast. Actually, you just have to be moving. Relative motion between you and the ruler, or you and a clock. But yeah, definitely great questions, guys. But note, all of the information that I was just talking about with length contraction and time dilation, at least relativistic time dilation, no longer is at play if you are in an accelerated reference frame. Or another way of putting that is if you're undergoing some sort of acceleration. Then you move over into the realm of general relativity, and you have to use the equations that define that that theory. All right, this illusion asks earlier you said it would be the speed of light for escape velocity from a black hole. But what about just getting near it and starting to get pulled in? Okay. So if you have not crossed the event horizon, if you have not crossed the event horizon, the well, if you've crossed the event horizon, there is no escaping. You are stuck within the black hole, and you will slowly or over some period of time will travel towards the singularity of the black hole. However, if you are outside of the event horizon, you'd want to use for your escape velocity equation, you'd use hmm, the escape velocity equation. I think would still be the same though, or better yet, let me be careful in saying that. The only time you'd want to use that v, I mean, use the fact that the escape velocity v is equal to c is if you're wanting to solve for the Schwarzschild radius. If you are outside the event horizon, you can go ahead and calculate what velocity will be required to escape the gravitational potential of the black hole. So the velocity would not be c, but the velocity would be whatever velocity is required to be able to escape the gravitational potential on you due to the black hole. So actually, let me do this. So I'm looking at the equation here, and I want to be able to show you guys. Or better yet, let's do this. So escape velocity. Let's see if I can get the equation for it. There we go. So in this situation, this is the equation you'd want to use to determine what sort of velocity you'd be required to escape the essentially the gravitational force that the black hole has on you, assuming of course you're outside of the event horizon. However, if you want to solve for the Schwarzschild radius of the black hole, you change this v here in this equation, it would become a c, and you'd solve for r. Good question, Hanny. So inside of the event horizon, all paths are basically towards the center of the black hole because not even light can escape. And light, as we know, is the fastest thing that moves in the universe. And so yeah, everything just continues to go towards its center. So there is no way out. And if earlier I did say that, I am so sorry that the speed of light for the escape velocity. What I meant by that was if you're looking to solve for the Schwarzschild radius, you'd have to replace the v with a c, and you solve for the r, and that would give you the Schwarzschild radius. Man, guys, this is some great questions. I'm realizing just how little I talk about these topics right now, and I'm actually happy to be able to talk with you guys about this stuff. So, how do black holes spin? Well, about the let's see. So, as far as the physical dynamics of the black hole spinning, um, I would imagine that in the process of being born, and I don't know the full dynamics, I don't know the full story of the dynamics, but I would imagine that in the process of being created, the the system from which the black hole is essentially made from was already probably undergoing some sort of rotation. So yes, angular momentum is probably going to be conserved in the process of producing the black hole. And you know what I'm realizing? I should probably keep my hands away from my laptop because I think that I'm also a part of the issue with the sound dropping in and out. So I'm seeing there aren't really that many more questions. Actually, I'll take this moment to actually take suggestions. Yes, yeah, I'm upset. I had gotten a mic and this mic is now dead, and I don't know how it died because I haven't done anything to it. Unless one of my kids got to it, then that could be an explanation. But but yeah, it's just my other mic is just kind of just sitting here doing nothing for me. So I have to use the internal mic for the laptop. You know what? I would try to play around with it and see if I can fix it, but I'm not too sure about it. I might just get a new one. It wasn't that expensive. But but yeah, guys, if you guys have any ideas as to topics that we can discuss, um, I'm more than happy to take those ideas. And hopefully, you guys just heard me just now because I saw that my connection kind of dropped to a low point there. I've had it now for a while. I've had it now for at least a few months. So I don't think they're going to take it take it back. But but yeah, if you guys have any ideas, because honestly, this discussion that we're having right now, was motivated by last week's discussion on colonizing the galaxy. So if you guys have ideas, send them my way, and I'll see if I can find a nice little problem to explain, and along with the science behind it. But the time is now 1:19 p.m., so I'm probably going to be wrapping up the stream pretty soon now. Well, guys, I love today's discussion. I loved all the questions. I had a really good time having this discussion with you guys, and I look forward, of course, to future discussions. And so I will be back on Friday after the Daily Space, which I'm not sure I might be giving. We'll see. um, thank you guys for coming, actually. And so I will see you guys on Friday. All right. Bye.